the lecture's on linear models and regularization. And let's see, so before we begin, there are some files that need to be downloaded for the worksheet. It's like 400 megabytes, so maybe if you guys wanted to do that now and get a head start on it. Raise your hand if you're using the binder Jupyter Notebook thing. Are you guys all running stuff locally on your laptops? Okay, so if you go into the day 4 L2 folder and open the one notebook you see there, if you execute the first few cells, I think the third cell there will download the 2 worksheets you'll need, or 2 data sets you'll need. So just give that a start, and then we'll get to the lecture. Any questions about that? Everyone found it? You know what I'm talking about? Great. Okay. So, linear models. This week we've been talking a lot about sampling, MCMC, nested sampling, and all these approximate techniques to figure out the posterior distributions for the quantities of interest given a data set. The cool thing about linear models is that if your model happens to be linear, you don't have to do any of that. There exists an analytic solution that if you type a couple lines of Python code, you can get the full posterior solution to your problem in under a second. So this has been really useful for me in my research, and hopefully you guys might find applications too. So linear model looks like this. You have some data vector, in this case, an array. This is like a light curve or gravitational wave, strength, signal, whatever. And we write that as the product of a matrix A and some vector of weights W. And this is the linear model. And so typically you also have some additive Gaussian noise when you actually make the observation. But the assumption behind a linear model is that everything you know about the system is a linear combination, some linear operation on a vector of weights. Now, I said that this is the data that you observe. This here is a vector of weights. Typically, these weights are the quantities of interest in the linear model. So for instance, if you're finding transiting planets, right, this would be some matrix that characterizes your model, and then this would be like the transit depth, the thing you're trying to constrain from your data set. This thing here is typically called the design matrix, or the matrix of regressors, different names for it. This is a really fancy way with matrices of saying essentially y equals mx plus b. Your data is linear. And in fact, one of the simplest linear models you can write is fit, say, a polynomial to data. So whenever you have a data set that, say, your model is just a polynomial, right? You might say you have some linear coefficient, or so some constant coefficient, some linear coefficient times x, plus some quadratic coefficient times x squared. I think we did this earlier in the week when you guys fit a polynomial using, I think, curve fit, or SciPy curve fit, something like that. The cool thing is that even though you have x squared, x cubed, this is still a linear model in these weights, and I can show you why in a second. So I can write this as the following matrix equation. I can say that y is equal to a matrix that looks like this. So the first column of the matrix is a bunch of 1s. The second column of the matrix is the value of x everywhere along, like, this could be time or this could be some other quantity, but the value of x evaluated at every point. And then the value of x squared evaluated at every point, and so forth. X cubed, x to the 4th. This is your design matrix, A. And then the vector of weights is just a vector of these coefficients. And so that would be C0. This would be C1 down to Cn. And this is what I call W. So that's how I would write the linear equation for fitting a polynomial to data. And in this case, the dimensions of my data, say this is a vector, it's a column vector. And so the dimensions would be, say, the number of points and points by 1. This design matrix is the number of points, the number of observations I make. Let's call it observations, actually. And so this is number of observations by the number of what we're calling regressors. Each one of these columns is something you're regressing against. And then this is just a column vector. It's equal to the number of regressors by 1. There's nothing profound here, but are there any questions about this setup? Cool. Now, another linear model that I've used in the past is for like detrending noisy observations. So I've worked a lot with the Kepler telescope and the K2 telescopes, same telescope, different missions, for finding exoplanets. And the story there, if you're not familiar, is that Kepler was at the time of the launch, and still is, it's the most precise photometer in space, whose purpose is to measure the brightness of stars over a period of 4 years, to look for transiting planets, to look for planets passing in front of the star, and you measure the transit depth, and you constrain the presence of a planet. Kepler light curves for like a typical solar-like star, an Earth around that star, would look like this. And so like every year or so, or every month, or however long the period of your planet is, you would see a transit, and then another transit, and another transit, and there would be some photon noise, right? All measurements are noisy. That's great. So Kepler operated for 4 years. It did a great job. It found thousands of planets. At the end of 4 years, two of the reaction wheels on the spacecraft broke, and a light curve that was previously like this, with K2, which was the second mission of the telescope, looked like this. It was still collecting data. It was still transmitting data back to Earth. And there were still transits in the data set, but now there was a huge noise component that was just added to everything. And the reason for this noise is that the telescope is no longer fixed on a patch of the sky. It's constantly drifting. And so it drifts and then needs to fire its thrusters to come back to the correct field and then fire again. And so every 6 or 12 hours, you would get these large spikes. Now, the cool thing is that this is happening to all stars in the detector. And so there's components of the noise, the same, whatever process is generating this noise, is affecting all the stars. And so there's a way to design one of these matrices, one of these design matrices, such that your regressors are some function of what's happening to all these stars. And so you can then solve this linear problem, which we're going to talk about in a second, to essentially find the weights. So you have a bunch of regressors, right? So like the flux in one star, the flux in another star, and another star. There's some linear combination of those vectors, given by this equation here, that when you subtract it from this data set that you measure, you get the thing you're interested in, the transit. So this is the process of detrending, and you can cast it as a linear model. There are all sorts of other linear models that you can encounter, but basically any model can be linear if you just Taylor expand it and drop all high-order terms. So even if your model's not linear, you can approximate it as so. Not always useful, but you can always do it. Okay. Questions about this so far? Yeah.
So what are the like family of functions that are like valid? Is it just polynomials, and like that's why you got to Taylor expand it, or is it like anything else work?
You can Taylor expand anything.
Like a sine and cosine is not going to work. An exponential is not going to work.
So, right. I mean, if the dependence is nonlinear on that parameter, it will not work, right? So if your model is like y equals exp of sine of x cubed plus square root of x. That's nonlinear in x, right? I could Taylor expand it, right? This is going to be approximately 1 plus some constant times x. And in that case, it's linear. But you're right. If your model is really complicated, it's not linear. I'll think of better examples that we can talk about too. Yeah.
So we had a question. How should we think about approximate versus, oh, I'm fired. How should we think about using approximate versus analytic methods? I.e., does there exist an enumerated list of inference problems for which closed form or analytic solutions exist?
So I really like linear problems because they make analysis very easy. Like, as we'll see, it'll take literally a second to get the answer. But there's some cases where the nonlinearities just do not allow you to make this approximation, and you have to use one of these approximate sampling techniques that we talked about. It depends on the problem. I don't know if I have any general advice on when this is applicable or not. Like, everything is linear locally, at least to some extent. And so in any case where a linear approximation is valid in the range that you're considering, this is a good choice. But generally, for really complicated systems, it might not be. There was a question back here.
So in the case of the trending, is y going to be the detrended light curve and a some sort of features of the original light curves?
That's right. That's right. In the example that I gave, my model, so the idea was that I have some data, and then I have some design matrix that captures something about the noise, and it can only capture stuff about the noise. It cannot fit the transit signal. And so whenever you try to model the data with this, it's going to only fit out, at least this is the hope, it's only going to fit out this jagged 6-hour noise pattern. And so the residuals, which would be your data minus this thing, will give you whatever the model was unable to fit out. And the hope is, and at least this worked for K2, that gives you like stellar activity or the transit signal or anything that's actually astrophysical and not part of your noise model.
Might be a little beyond, but what's usually the features that you use for the design matrix?
There are different things you can do, and there's an example that I'm going to go over. Okay. Right? The simplest thing is maybe you have a telescope on the ground, and it's observing, and you see some noise. But you also have simultaneous measurements of like the humidity, or the temperature, or the air pressure. And these are all things that correlate with the measurements that the telescope is making. And so those would be valid things to put in your design matrix. If you work in the stock market, this might be familiar too, because you're trying to predict the value of the stocks on a given date, and simultaneously, like, you have measurements of, like the weather, or like what's happening on Wall Street, or what's happening politically, or you have like whatever tracers of the economy. And so you can put those in your design matrix and try to build up a set of weights that combine those to give you a prediction for what the stocks are doing. And so it really depends on the problem, but you're typically looking for any kind of process that you can measure and it correlates with the thing you're trying to model in a linear way. But we're going to talk more about that later. So I have 15 minutes, about 10% of the way through. So in the interest of time, and I need to get the regularization too. This is going to be interesting. But in the interest of time, what we're trying to do here is we have that equation, y equals a dot w. We're interested in finding what w is, the weights. We want to solve this. So for instance, in the simple case where we're fitting a polynomial, we want to find the polynomial weights to find the best fit solution. Now, it would be awesome if I always break chalk, sorry. If I had y equals aw, and I could just do this. Essentially divide both sides by a and solve for w. Why is this a bad idea? Or why might this not work in practice? Yeah.
Because it's hard to invert matrices.
It can be hard to invert matrices if they're really big. It might also be impossible to invert matrices in many cases. And why might that be? Yeah.
Basically because it's not a squared matrix.
Exactly. Your matrix is not always going to be square. In the case where, say, for example, say I have 2 data points. That's my y vector. I've made 2 measurements. And say I want to fit a 20th order polynomial to these 2 data points. My design matrix, will look like this. So it's a giant rectangle. And then my vector of weights will look like this, 20 weights. I'm trying to invert this thing. There's no solution. You can only invert square matrices. Even when your matrix is square, it doesn't always have an inverse. So if I have, we'll get into that. You can't do this, unfortunately. However, there is a way to solve this. But we could also always do MCMC. We could resort to some approximate sampling technique, right? We could define some log likelihood function like we've been doing this past week. And if you remember my lecture in Pittsburgh, the log likelihood function, if your errors are Gaussian, looks something like this. It's -1/2 your data minus your model. In this case, we have a linear model, so it's AW, transpose. Times some covariance matrix. This, typically, whenever we make an observation, usually, is a diagonal matrix, and the entries are just the standard deviation squared, or in this case, the inverse of the standard deviation squared, dotted with y minus AW, plus some constant. Raise your hand if you've seen this before, if you remember it from my lecture, or if it looks familiar. Okay, most of us. If you've never seen this before, this is essentially where chi-squared comes from. If you've ever done chi-squared to try to compute some goodness of fit metric, you are taking your data, you're subtracting off your model, you're squaring it, right, this times this, and then you're dividing it by the standard deviation squared. And then you're summing over all of it. As a matrix equation, that's exactly what this looks like. So this is just chi-squared. But more formally, it is the log likelihood under the assumption that your noise is Gaussian. Okay. Now, the cool thing about a linear model is that it's a convex model. And what that means is that we're trying to find the value of W. And remember, W is a vector, but since I can only plot things in 2 dimensions, it's a scalar here. So say this is W, and say this is the log likelihood. There exists some value of W that maximizes this log likelihood. And the cool thing about convex problems, such as this one, is that there is only one solution, and there's only one single peak. And so everywhere the gradient of this function points towards the global solution. A lot of problems are not this way. A lot of problems have many solutions. A lot of problems have many peaks, many modes. Talked about those with nested sampling earlier in the week. But for a linear problem, your space looks like this, looks convex everywhere. It's well behaved. Now, we probably remember this from high school or maybe the beginning of undergrad. If I have a function, and I know it only has a peak, it doesn't have any value or anything, how do I find this point? What mathematical operation do I do? Derivative, yeah. So the cool thing is that at the peak, the derivative is 0. And we know that because it's convex, that's only true at the peak. And so if we take the derivative of this thing and set it equal to 0, we will get the best fit solution for W. So I'm going to call that W hat, is usually what it's called. Now, I only have 10 minutes, so I'm not going to do this derivation, but you can try it out on your own if you'd like. And you'll have to trust me right now. But if I take the derivative of this with respect to W, and set it equal to 0, and then solve for W, the answer that I get is the following. I get that W hat is equal to A transpose sigma inverse A inverse A transpose Y. And we're done. This is a matrix product, matrix product. You have to take a matrix inverse. If your problem's large, like in the problems I was addressing with K2 and detrending, these matrices were like a few thousand by a few thousand. Modern computers can do that in 100 milliseconds. And then you have another matrix product, and then dot it into your vector. So I can find the global optimum in under a second on my computer. Someone wasn't paying attention. Dan. You saw it? Okay. All right. Sorry. Good. And the way I remember this, by the way, is the following. We can't do this. That's not allowed. But what we can do is a trick. We can multiply both sides by A transpose. I can do that. Given any equation, I can multiply both sides by whatever I want. As Dan says, you can't stop me. And the cool thing about this quantity here is that any matrix transposed and dotted into itself is a square matrix. And so I can hopefully take its inverse, not always. So that's another way to get the exact same thing, except in this case, I haven't said anything about the noise properties. This is effectively the same as assuming that my covariance matrix is just the identity. Note that even if it's not the identity, if it's the identity times some value, which is essentially the same as saying that the error bars are the same everywhere, which is a frequent assumption. I have the inverse of the inverse multiplied with the inverse. They actually just cancel out, so you get this exact same result, regardless of the magnitude of your error bars. Did that make any sense? It made some sense. That's good. Okay, I showed you how to optimize this log likelihood. Bless you. But this entire week we've been talking about probabilities and posterior estimates. I've said nothing about my belief, the degree of my belief in this value that I found for W. Now the cool thing about linear models is that not only are they convex, but under a suitable choice of prior, I'm going to talk about that in a second, the posterior is a Gaussian. And so it's fully characterized by the mean, which we just derived, and the standard deviation, or the covariance matrix. And because linear models are awesome, and Gaussians are fun, and everything's easy, this here is your covariance matrix. And I don't have time to derive it, but the trick is to take the second derivative of the likelihood. The second derivative of a Gaussian, with respect to the mean of the Gaussian, is the covariance of a Gaussian. I'll leave that as a homework for people to prove. But the covariance of this estimate, which again is like your error bar on W, is just A transpose sigma inverse A inverse. And we're done. If I were to put this log likelihood into MC or PyMC3 or nested sampling, and I give it my data vector, and then I solve for these W, for these weights, try to get a posterior estimate, I will get Gaussian posteriors. They're all going to be, and I run it for infinity, right? I have to run it for an infinite amount of time. All the W's are going to be Gaussians, and their standard deviation are going to be the diagonals of this matrix. So if your model's linear and your errors are Gaussian, you don't have to do MCMC. That's the beauty. You can just invert a couple matrices and get your answer and publish your paper. and get famous. I have 4 minutes and 49 seconds to tell you that I have made a very big omission so far. I'm talking about likelihoods and posteriors, but I have not yet talked about often what is an extremely important part of inference, and it's the prior. What prior have I assumed in deriving this? Yeah.
Gaussian?
Yes, but what is the variance of this Gaussian? What is the mean of the Gaussian prior that I assumed?
Mean would be 0.
The mean is 0, yeah, good.
The standard deviation is symmetric? Like the distribution is symmetric?
It is, it's a Gaussian, so it is symmetric. Okay. I haven't said anything about a prior. It looks like I'm even not using a prior. That's never true. You're always using a prior when you do inference. It turns out that in this case, the prior that I'm effectively using is a Gaussian prior on W with 0 mean and infinite variance. And that's because, remember, so like, this is my log likelihood, and so my log probability is the sum of my likelihood and a prior. I'm sorry for those of you who need to write this line again in their notes, and I can just erase it and switch it with a P. To add a prior to this, I need to add a term that says something about my belief about W before I make the measurements. And let's assume it's a Gaussian, because we have a linear model. If we assume it's Gaussian, things stay analytic. That's how I would add a prior to this, right? So like, here's my likelihood term with the data. And then this is just saying that I believe that W has some mean, which I'm assuming is 0, and some variance. If this thing is infinity, and I invert it, this is just 0. And I get to this. If I have infinite variance on the prior doesn't tell you anything. It's in fact the same as assuming a flat prior, because as I make this Gaussian infinitely wide, my prior density everywhere is just flat. But often you do want to use a prior, and one of the reasons in a linear model when you absolutely have to specify a prior is that, sure, this thing is square, but I still haven't convinced you that it's invertible. And it's actually usually not invertible in a lot of cases. If I try to fit 2 data points with a 20th order polynomial, right, it's that weird rectangular matrix, really skinny one, or really short one, wide. If I dot it with itself here, sure, I get a square matrix, but it's definitely not invertible because I do not have enough information coming from my data, I only have 2 data points, to constrain the 20 parameters. This is a classic overfitting. And so I need a prior. And this is where regularization comes in. So the main topic of my lecture will be delivered in the last 50 seconds. And the idea is that if I now do the same procedure, but this time explicitly account for the fact that I have a prior, I just wrote this, I didn't say anything. This is the prior variance, prior covariance matrix for W. I don't know why it's capital lambda, it just is. It's to distinguish it from sigma, but it is also just a covariance matrix. If I go through the same experiment, and you can do this at home, I will find that the only change I need to make to these equations is the following. I still have the fact that W hat is A transpose sigma inverse A inverse A transpose sigma inverse Y. And I still have that sigma W as The only change that I have to make is the following. And we're done. So you can show that by doing these same steps, right? Setting the derivative likelihood with respect to 0, solving for W hat, do a little algebra, you'll get this. The prior just very naturally comes into the covariance matrix. Now, a lot of times, if I'm fitting a polynomial to data, say, to prevent overfitting, and we're going to see this in the example in just a second. Okay, my time is up, but I'm going to take another minute to finish this. Typically, one common choice is to just say that this matrix here is just some number times the identity matrix. That means that I'm putting the same Gaussian prior on all my parameters W. Or maybe it's a diagonal matrix and every parameter has a slightly different variance. It doesn't matter. Typically, this is a diagonal matrix. And so the cool thing here is that if I have a matrix that's not invertible because my data is not constraining enough, this matrix is singular, right? By adding a prior, that corresponds to adding entries to the diagonal of this matrix. And by adding entries to the diagonal of the matrix, I'm making it more dominant along the diagonal. If this is large enough, my matrix will be invertible because the identity matrix is invertible, trivially. And so there's an interesting story here. It's like back in the 70s or 60s when people were starting to invert large matrices on computers, they realized that matrix inversion is hard. It's numerically unstable. They realized that by adding small elements to the diagonal of their matrices, they were able to invert them suddenly. And it wasn't until afterwards that they realized that this is exactly what you get if you're a Bayesian, if you believe that your probability is the likelihood times your prior. You go through this matrix algebra, and you get an estimate for W. Okay, questions? Rocio.
I'm having trouble interpreting the lambda, the covariance of the prior.
Mm-hmm.
Like we said, the covariance matrix for the data are the errors. What is the interpretation for the prior covariance?
That's a great question. So what is the interpretation for the prior? Is if I have any information about the parameters that I'm trying to constrain before I collect the data, that goes into lambda. Now, in the example we're going to see in just a second, if we have a lot of parameters and just a little bit of data, one typical choice is to just, you want to, without assuming this prior, your prior variance is infinite. You just want to make it small to the point where this matrix is invertible. So one of the points of regularization and ridge regression, which is what this is to shrink your values of W closer to 0. One of the classic problems of overfitting, and we're going to see this in just a second, is that if I try to fit a very large order polynomial to just a little bit of data, you'll see that I get a perfect fit, but it's pretty useless because my model goes through every single data point and has no predictive power. This happens because my values of W get extremely large. You'll see that my coefficients for W, if I'm fitting a polynomial, are going to be like 10 to the 40, 10 to the 39. That's probably not what we want. We probably want values that are much closer to 0. And so this is called a shrinkage prior, in that by assuming a small variance for these values, I constrain them to be close to 0. That's in the case where like you kind of don't care physically for what the values of the polynomial coefficients are. You just make this small enough to the point that you prevent overfitting. But oftentimes you do care, right? Like the parameter you're fitting for is, say, like the depth of a transit. We're going to see that in a second. I have some prior information about this transit. Maybe I know it's a rocky planet, and so maybe I know the depth has to be 100 parts per million plus or minus 50 parts per million. That's a physical way of interpreting what this thing is. And by the way, right? The variance is just the square of the standard deviation, the width of the Gaussian. Okay. Let's start the worksheet because it starts with an example.
And as a brief reminder, we will be working on these problems together. So if you don't have a partner, someone that you're sitting next to, please rearrange yourselves, appropriately. Thank you.
Okay. Were people able to download the CSV files? Raise your hand if you had trouble. Are you still having trouble? All right. If you had trouble, silently troubleshoot with someone sitting next to you. Okay, so let me just have all your attentions for a second. So we begin with problem -1, which is fitting a polynomial. So if I have a data set that looks like this, is what I've been talking about. I have 15 data points, and I believe that there is some trend here. Maybe it's linear, maybe it's quadratic, maybe it's cubic. I do not believe that it is a 15th order polynomial. I do not want a model that goes through every data point. But we can still play around with it and see what happens. So if we execute the first few cells, you should see a little widget pop up where I have a model and I am fitting a polynomial of some order. And as I step through the order of that polynomial, we can see I get progressively better fits, better and better and better. The chi-squared is going down, down, down. The model is getting closer and closer to the data until the point where I get a 14th order polynomial, and you can check that it perfectly fits all of the data. But this model is telling me that if I were to make a measurement of whatever this is, doesn't matter, if I were to make a measurement right here, the value would be like 15 or 1,000,000 or whatever. I don't think that's true. I don't think this model actually describes the true correlation between the data points. And so I need to regularize. And so that's what this next step does. And you can look at the code. We'll do that in a second. But if I execute this, I now have an extra little widget down here that controls the variance, which is what Rocio was asking about, that lambda parameter. In this case, it's the log of the variance. It's how big I'm allowing those coefficients to get. And if I fix it at 5, you can play around with this in a second, you can see that as I increase the order polynomial, I start getting better and better models up to a certain point. Right now I'm getting to 8th, 9th order, 10th order. I'm increasing the number of parameters in my fit, but I am not overfitting. So by choosing an appropriate prior for these coefficients, I allow the model to stay physical to some extent, to the extent that I can actually interpret what this variance means. Now you can play around with this. If my log variance goes to 0, what's going to happen to this line? Predictions. Yes? What? It just becomes the mean. It just goes to 0. So we can actually verify this. If I go it all the way here, I am regularizing so strongly that I'm saying no matter what the data is saying, I do not believe W is anything but 0. If, on the other hand, I allow my variance to go to infinity, I should recover what I had before, which is the unregularized solution. The truth is probably somewhere in between. I don't have time to talk about this, but there's a whole art and science that goes behind actually figuring out what the appropriate variance is for a problem. Sometimes you have a physical interpretation, right? So like if you're fitting a transit model, you have some idea what the depth is going to be. It's not going to be more than the depth of a Jupiter. It's not going to be less than the depth of a Mars-sized planet, maybe, depending on the problem. But often you don't know, right? If I'm running the Everest model where I'm detrending data, and my coefficients are just weights of how much this systematic contributes to the noise that I see, I don't really have a physical intuition for what that variance should be. And one of the things we can do, I'm just going to give you a term to search, because I don't have time to talk about it. One of the things that you can do is do this thing called cross-validation. And this is popular in machine learning. You may have seen this word before, but the basic idea is that it's one of a whole class of schemes where you hide data points from your model, and then you suddenly introduce them, and you see how well the model predicts those data points that you withheld. And if it did terribly, it probably means you're overfitting. If it did okay, it means your model is probably behaving the way it should. Okay. So play around with this a little bit to get a feel for what regularization is actually doing to the problem. The cool thing about regularization is that it's different. Well, one way to regularize is to just use a low-order polynomial. You're explicitly saying all high-order polynomial coefficients are 0. They have 0 variance. That's one way to regularize. But the cool thing about this way is that you still allow the model to have 14 wiggles. You're just limiting the extent of those wiggles. Hogg always says, and I really like this, that a Gaussian process, you can mathematically show that a Gaussian process is a very, very well regularized infinite order polynomial. This, I mean, you know, for a certain value of the variance here, this kind of looks like what a Gaussian process might output. And there is an intimate mathematical relationship between the two. A Gaussian process is this non-parametric thing that is very specially regularized. And you control that with the amplitude of the kernel. Okay. Before we go on to this problem, I just want to bring your attention to the following. So in cell number 5 here, I just want to show you how I'm computing this model. I didn't use curve fit for this example. I just used the equations that we derived here. I constructed my design matrix here using, you won't need this for the problems you're about to do, but the Vander function constructs the Vandermonde matrix, which is literally just a matrix whose first column is 1s, second column is x, third column is x squared, fourth column is x fourth. It's just, you could code this up yourself in a couple lines of Python. This saves you time. Don't worry about it. The important line is right here, where I have my design matrix. I transpose it. I dot it with itself. You remember that from my lecture. And then here, I use np.linalg.solve c comma a transpose dot y. np.linalg.solve is solving this problem. Right, np.linalg.solve c comma a transpose y. And note that I'm not explicitly taking the inverse of this matrix because taking matrix inverses is hard. It's numerically unstable. It's much easier to directly compute this than to first invert this and then dot it with this. So that's the line you should base your answers to the next two problems on. I'm about to throw you guys in. Any questions? Someone stretching? Just stretching. Okay. So the problem you're going to do is essentially what I did with Everest, because that's all I know to talk about. And it's the following. I claim that there is a transit hiding in this data set. This is a light curve, 27 days, kind of like TESS. A light curve of a star, and there's a lot of stuff going on. Maybe it's stellar variability. It's not. It's all instrumental variability. This is synthetic. I made this up. There are lots of things that look like they could be transits, right? Maybe that, maybe that, maybe this giant thing. I'm telling you nothing about the size or the shape or the position of this transit. The way you're going to find it is the following. In addition to this light curve, you can see that in the data set that I gave you, I'll show you how to import it, I have these housekeeping variables that I believe correlate with the systematics model. So I have some measurement of the temperature, the cloudiness, these numbers don't really mean anything. Maybe it's log cloudiness. Whatever. The stability of the piston, the humidity, the air pressure. It doesn't matter. It doesn't matter. It's made up. But this is how linear models work. So if you plot the... What's so funny? I wanted to do one which was like, like the sleepiness level of the telescope operator. There are negative clouds in space. Yeah, so it's tests. You're good. What are negative clouds? Okay, all right, I'm good. It is tests, great. So notice I'm constructing my design matrix here by just horizontally stacking these regressors, 5 of them. And if I plot each of those columns, I get things that suspiciously look similar to the light curve itself. So our assumption that they're controlling the noise there is probably correct. It is, because this is a synthetic problem. But now, all you're going to do in problem 1 is construct your linear model out of this design matrix, subtract it from the data, and then look at the residuals and try to find the transit. And I want to know where the transit is and how deep it is. In the second one, in the second problem, you're again given a similar light curve. But this time, you don't have 5 regressors, you have 500. As the number of regressors increases, it's kind of like fitting a very, very large polynomial. You're probably going to want to regularize. So you're probably going to want to add something to the diagonal of that covariance matrix. Go. Okay, everyone, let's go over the answers. Thanks. You will see that as before, the answers are right there in the repository. So if you just go to the answers folder and open up the notebook, they're all there. And so if you did problem 1, you should see that the transit is not at all where you might think it was ahead of time. It's right there. That doesn't even look like a transit. But this is something that happened to me when I was developing Everest, is that the noise is so much stronger than the astrophysical signals that you're interested in, that you really need to do something like this in order to even see the transit. And so if you did it properly, you will see that your model is able to predict your data really well everywhere, except right there. And if you look at the difference between your model, which is made only of systematics, only of noise stuff, if you take the difference between that and your data, you get residuals that look like a transit. And so that was the goal of the first problem. And again, in this first problem, we didn't do any regularization, and we didn't have to, because we have, I don't even know how many data points we have. We have like tens of thousands of data points, and only 5 regressors. So that's equivalent to having like a really big data set and fitting like a 5th order polynomial. You're not going to overfit because your model is just not that flexible. So this just worked. Any questions about this first problem that people had? Okay. In the second problem is the exact same thing, except this time we have 500 regressors. And if you were to repeat the exact same procedure, if you were to repeat the exact same procedure, where you don't have any regularization, you will find the weights actually get fairly large, and then your model will perfectly fit the data. And then if you look at the residuals, you should essentially, well, you get a model that goes through the data everywhere, and then your residuals look perfectly flat. That's what happens if you have no regularization, because you have all these regressors. They all want to collaborate and contribute and bend backwards and fit the data as well as they can, and that's exactly what happens. And so when you have a lot of regressors, a really large design matrix, you have to add some regularization to limit how flexible your model is, because you don't want to throw the baby out with the bathwater, as it were. And so and so the trick, as we talked about earlier, is to add a prior, is to essentially say, okay, I'm going to keep all the regressors, but I'm going to limit what their weights can be. And that, in the simplest case, is as simple as just adding a small term to the diagonal of your covariance matrix. Some other things that people were talking about is maybe I can reduce the size of the design matrix. Maybe I can only keep 5 of the regressors. Sometimes that'll work. In this case, it won't work because the way I constructed the problem was I built the noise out of all the regressors. And so there don't exist just 5 of them that will explain all of the noise in the data. You have to use all of them. One thing that could work, though, is to do something like PCA, right? Try to look at all the columns of the design matrix and pick out the common features. Do PCA, keep only 5 or 10 of those components. I suspect that would work. I haven't tried it. But if you would like to do that, that might be a fun exercise. The easiest thing, though, is to just add these terms to the diagonal matrix. And the way that looks like in practice is here. So I still have the same A transpose A. Here I'm dividing by the uncertainty squared. Some of you didn't include that sigma, which is fine, because you'll notice that I made it very easy for you guys. And I gave all the data points the same error, which is 1. And so that's really just the identity matrix. In this case, your covariance matrix is truly the identity matrix. So whether you use it or not, you get the same answer. Not always going to be the case. So remember to put your sigma inverse in there when you do this in practice. But if you add an appropriate amount of regularization, and there's no right answer here, because this number is made up, but I use 10 to the minus 5 for lambda. And when I do that, we can see a feature stick out here. And the transit is, in fact, this thing right here, which you can see by eye, but you don't necessarily know it's a transit ahead of time. But you can see that the model is struggling to fit this data point. Now, if you zoom in, you'll notice that there are these wiggles on either side of the transit, which are not real. These are artifacts due to the fact that the model is trying to fit out the transit. We have 500 parameters. That's a lot. Even with regularization, you can overfit this a little bit. And this transit is actually shallower than it should be in practice. So far, what we're doing is we're detrending, right? We have some data set. We have some model for the systematics. We apply that model. Physically, what that means is we subtract that model from the data. And we hope that the residuals have kept, that the model has not touched the signal of interest, that the residuals contain the transit. That's not always going to be the case. Even if your model's regularized, and even though the systematics are not the same process that's generating the transit, you have enough regressors, they can start to fit out the transit. So the proper thing to do, or one of the proper things to do, is to simultaneously fit the systematics and the transit. And in this case, this is easy to do. It's still a linear problem because I tell you, this isn't true in general, but in this case, I'm telling you where the transit is, and I'm telling you that in this case, it's just a Gaussian. And the only thing that you need to find is the depth of the transit. If all you need to know is the depth of the transit, that's a linear problem, right? It's just some scale by which I'm multiplying this function. I have 26 seconds, and so you can look at this code in your free time. But the trick was to add the regularization and let's see. Here. So you had to add an extra term to your design, to your regularization matrix here. That was the prior variance on the transit. If you didn't account for that, you would end up regularizing the transit as well and forcing it to be really small, and you wouldn't see it. But if you did it properly, you would find the correct transit depth, which was something like 6.5, I think. And you can see the transit model right there. And you can see that when we simultaneously fit the transit and the systematics will not touch the transit because there is a better model, there's a better regressor that better explains what the data is doing in this vicinity here. And there's our beautiful transit. We're out of time, so thank you, guys.